Thank you, Cooper, and thank you, Dylan, for this opportunity to present my talk in Hacking the Box. And thank you for all the audience for tuning in to this online session. As it's the first talk of the day, let's start with a quick mind teaser. How to find local elevation of privilege vulnerabilities, specifically speaking on Windows. There are four answers. Is it fuzzing, B, fuzzing, C, fuzzing, or D, fuzzing and symbolic execution? I'm not here to talk about fuzzing or rather symbolic execution or any other approach that works with fuzzing. Here, we will present a different approach to find security bugs that I've developed, which I called MTE. MTE stands for Monitor, Trace, and Exploit. In the essence of it, you monitor every privileged process that runs on the system, followed by tracing its file operations. If the privileged file operations are not done with care, we might exploit them with two simple file manipulation attacks. You're probably familiar with them. They're not that new. DLL hijacking goes back to the year 2000, and James Forshaw first presented the abuse of object manager symbolic links in the year 2015. Still, by using those two file manipulation attacks automatically, I found many bugs across many different vendors. Now, a bit before we dive in, I'll present myself. I'm a security researcher at CyberArk. I tend to focus on Windows primarily at discovering logical bugs, specifically privilege escalation. While I do look at other platforms, Windows is my bread and butter. And besides that, I'm notoriously known to blue screening my own device in bad times, so I really hope it won't happen now. And I also really enjoy making and mixing cocktails, and I hope you see that there is a connection between those two. So what are we going to talk about? We will see how one might easily make use of symbolic links for elevation of privilege attacks, followed by looking at how you can do something I call lazy privilege escalation, waiting for privilege code to load resources from unprotected directories, which are directories a regular user has the permission to write into. And we will see how we can take advantage of that. After that, we will visit MTE and see how that we can reliably check if privileged processors are vulnerable to file manipulation attacks. I believe you will see that finding elevation of privilege bugs in mass is not that difficult, and you can probably achieve the same result yourself. You only need a way to properly define when a program is vulnerable to file manipulation attacks and how you can automate the entire exploitation process. Now, this slide is a slide that you almost find in any privilege escalation talk. Microsoft usually divides security boundaries as a separation between the user's privilege levels. In Windows, privilege violation is a sort of a perspective of how an attack might be where an attacker wants to move between privilege levels. So anything which consists moving up the privilege level could be arguably considered bypassing security boundary. So this is a place where if you can move around will cause vendors to fix it, presumably. Every vertical jump in the hierarchy would most likely end up with a CVE, even by the most demanding standards. Aside from the transition between the administrator to the kernel, which is not considered a security violation by Microsoft, which is a thing I don't entirely agree with, but nevertheless what we can do. This also includes UAC bypasses for all that matters. I said Microsoft before without mentioning other vendors thus far, because they're considered to have a firm definition of what a vulnerability is. As a result, many vendors inherit their definition of security vulnerability. In my research, I focused on the escalation from a local user into a privileged user, which is from a non-admin user to an admin or a local system. So all the vulnerabilities that I discovered among those that were found manually and those that were found automatically are elevation of privilege vulnerabilities. Interestingly, every vendor that I've checked had at least one vulnerability of this type. Now, this diagram roughly describes the proportion between different vulnerable software. This also shows our attack surface. Because we are after elevation of privilege vulnerabilities, we must target privilege process. That's the only way we can do it. I was mainly looking at the beginning at system services due to their relatively high privilege level. Although they had their share of problems, installers and update programs were a lot more vulnerable to file manipulation attacks. This is mostly because of their nature. Installing and patching software often involves doing many I/O operations, which could be taken advantage by using R2 file manipulation attacks. Now, if the word symbolic link sounds familiar, it is because this concept exists on Unix platform for many years. On Unix, a symbolic link are files that contain a path of the file they point on. So when the kernel tries to access the symbolic link, it will parse the value in the symlink following the path of the symbolic link. On Windows, on the other hand, symbolic links are a different thing. At the beginning of the joyful NT3 days, we only had object manager symbolic links and registry symbolic links, but we don't care about them now. An object manager symbolic link is an object that is used to translate a reference to one named object into another name. When created, it links the name of the symlink to the name of the target object. The target object can be of any type of the object type the object manager supports, including another symbolic link, and it can go on and on and on. This type of link was supposed to be used by driver developers and by system only. The second, or rather the third type of symbolic link is the NTFS mount point, or directory junctions. There is a small difference between. NTFS mount point were first introduced in Windows 2000. They allow the system to have a directory-like symlink. Now, both the creation of symbolic link and NTFS mount point do not require special privileges and can be done by a regular user, a thing that is not true for NTFS symbolic links that were presented only in Windows Vista. Those are real file system symbolic links like the ones on Unix. But they do require administrator privileges to create them, so they're not that useful in the eyes of elevation of privilege attacks, while the two previously mentioned, Object Manager symlinks and NTFS mount point, do not require any privileges. Here is a snippet of a popular tool in the sys internals called WinOBJ, which showcases us the Object Manager file system. Now, the Object Manager has a different subsystem than the regular file system, and it resides in the Windows Executive. Its main job is to maintain the system-wide catalog of all objects in the system. Another job of the Object Manager is to parse names passed by it by the I/O Manager whenever a create file request is received. Now, the Object Manager namespace is organized in a hierarchy tree. Each level is an object of the type of object directory. Each object directory has a name and can have multiple nested object directories within. And it all starts with the root directory, \. One of the most important directories in Windows is the C-column directory. The C-column directory is not a real directory on disk. Instead, the C directory is just an object in the Object Manager of the type of symbolic link. The object that holds the value of path of the device, the hard drive in our case, C-column is reparsed to \device hard disk volume 4. So every time you do a file operation on files that reside inside the C volume, you get the value of the symbolic link. Now, every object directory is a secureable resource. So not everyone can access objects in the Object Manager namespace, which of course makes sense. But if you could alter the values of some of the symbolic links objects, what can we do? It turns out there is a place that we can do some attacks of this nature, which is \rpc control. We will see shortly how to do so. But let's see what can we do if we can actually create Object Manager symbolic links and a mount point. Now, the first bug is creating a file in a protected directory without having the rights to do so. If we find a privilege code that does a create file operation inside an unprotected path, which is, as I said before, a path that anyone can create files there, we can create a mount point with a symbolic link, and the service will reparse the symlink the create file operation, and we can achieve arbitrary file creation in arbitrary locations. We also can alter the file name because we can give any desired name of a symlink inside the object manager. Now, this is somewhat limited in case of privileged code does not alter the ACL of a newly created files because we are not guaranteed to be able to edit the content of the file eventually after it's created. Also, finding privileged code that does a create file followed by a write file operation, we gain arbitrary file creation and arbitrary write, which is a lot more useful if we want to change protected folders or to create new files altogether. Of course, this is a lot more useful in case we want to fully escalate our privileges. And finally, if we see an anti-malware solution or just any privileged entity for this regard trying to delete a file, we can exploit it for arbitrary delete. We will see a short example of this later. So if we wrap everything up, with an arbitrary create, we can do file spotting attacks, like creating files that were mere exist and will crash the system. Like in this case of this DLL. Please do not try it on your home PC, only in a VM. It requires physical access to fix the blue screen that you will have later. If we have arbitrary write, then we can create our malicious DLL that will be loaded by a local service. There is a fairly large number of DLLs that you can use that will be loaded by local services. This is because many services look up for DLLs that do not exist on their current folders. And if they do actually exist, they load them happily, and you can easily escalate your privileges into the level of the system user. So this is a pretty reliable way to do it. In this case, this DLL is loaded by the Windows Error Reporting service. Lastly, arbitrary delete is a kind of a mixed bug. You can surely deny service the system and tamper with anti-malware solutions, but fully escalating your privileges is not that easy. But having the ability to delete system files can help you with other primitives. Let's see how it's done. The first thing we want to do is to create a mount point. We take advantage of the fact the object manager has a bunch of object directories. Since there is an object directory, we have some permissions on it that we can create new objects there as a regular user. We can create a mount point from the regular file system into the object directory called \rpc control. We basically create a mount point on the local directory that will link into the object manager namespace. By calling a create directory simple API, followed by calling device IO control with a set reparse point flag, we can achieve this trick. Now, it cannot be that easy, right? Well, we have some limitations. The directory must be cleaned. We need to be able to delete any file that resides inside the directory to change it to a mount point. Therefore, we need to have permission to delete every file in there. Also, we need to have the right permission over the directory. Interestingly, we do not need to have full permissions over the directory. Like, we do not need to have the delete permission on the directory, a thing which is very useful in many cases because there are a lot of folders inside Windows or the System32 directory that you only have the ability to create files there, but you do not have the ability to delete files there, and you cannot delete the directory, but you can do other things with it. Now, the second thing that we need to do for a successful attack is to create an object manager symbolically. The great thing about it is that anyone can create them. Unfortunately, you are somewhat limited to the namespace selection, and you cannot create a permanent symbolic links. This is because it requires admin privileges to do so. Sadly, if those symlinks are not permanent, they will be deleted if every handle to this object is closed. Therefore, upon a restart, the symlink object will be gone. So this is not a very good way to persist the local system if you're a malware, because you probably do not have administrator rights. So you can do other things, but this is not that useful. Still, this is very good in the eyes of elevation of privilege attacks, because most of the time we have enough time to set up our symbolic links. so we don't need them to work from the start. Now, let's see how actually the path translation works under the hood. If we take a look how the service that tries to access cdir_file.txt, and the attacker created a mount point on the dir directory and a symlink of file.txt. Now, we start with the call to RTL-DOS pathname to NT-pathname API. This just changes the Win32, or rather the DOS name, to its NT path notation. Now, the object manager takes the input name, the NT path, and parses its components, which are separated by a backslash, until it finds all the objects that are a target of the request. So basically, every component of the path will be called with a lookup function, with the OBP lookup object name, API, in the kernel. So in the object manager, actually the C directory will get the value of the path we saw earlier, which is /device/hard disk volume4. The dir directory, on the other hand, will be translated to its mounted directory, which is the object directory /rpc control, which we have the permissions to create symbolic links in there. And the file name, file.txt, will be translated to the symlink we created. In this case, the symlink value is cwindows.ext.dll, the DLL we saw earlier. So the create file operation, the service thought it did on cdir_file.txt, will eventually resolve to cwindows.ext.dll. Now, let's go through a real example. This bug is in the Windows Defender and in the way it updates signatures. As you all know, Windows Defender runs in the privilege level of anti-authority system. It must do it in order to carry its duties as an anti-malware solution. Because this product is so complicated, it has many models. One of the models, which is called MP6 stub, is also runs in the same context of the Windows Defender, and it is responsible for updating, downloading, and extracting signatures to the anti-malware engine. Now, it does the entire operation in the local app data folder, which is, of course, not a protected folder because the local user can access there. And it does the write operations and delete operation of signature files inside the temp MP telemetry submit. Now, it sounds good on paper. It does the write operation and delete operations. But the delete operations on specifically saying the client manifest.txt suffers from some problems. Now, this problem is quite familiar, and it's because of badly used access tokens. Now, on Windows, every process has an access token, and specifically speaking, a primary token, which holds the security context of the process. Each thread has a copy of this primary token. This is because whenever a thread tries to access a resource, it must provide its security context. Also, threads might have another type of token called impersonation token. This token is used to impersonate other users. This allows a thread to act in a different context than the primary token context. In our case, the thread that was responsible for the write operations indeed impersonated the local user, which means we cannot take advantage of the fact the process is privileged and does a write file operation in unprotected place. But the thread that did the delete operation of the client manifest.txt file was indeed privileged and did not impersonate the local user. Therefore, when it did the delete operation on the file, we can actually take advantage of it because it's used its primary token instead of the impersonation one, which means it fits great to our attack of creating a mount point and a symbolic link. Now, let's see a recorded demo of it. Because it's an online session, I allowed myself to record the demo because too many things can go wrong. So, as you can see, we have a terminal with a currently logged on weak user that only belongs to the users group, we activate our exploit that tries to read from cwindowskey.txt, and this file indeed exists. We activate the update routine signature of the Windows Defender, and we can see that it deleted the file called key.txt. We just created a mount point and a symbolic link, and that's it. We were able to do an arbitrary delete attack with the privilege of Windows Defender. So how did Microsoft fix it? And what are the general mitigations to this type of attack? For starters, we can just make sure the directory that holds the client manifest.txt to be admin ACL. Preventing a regular user from having write permissions will break the first part of the attack, which is creating a mount point. If you cannot create a mount point, you cannot proceed with the attack. Besides that, every privileged software should be taken impersonation seriously. If your process is privileged and you must do file operations on user-owned resources, you must know which tokens your threads use. Not unlike this CVE, which is actually the first vulnerability that I found in this research, which was also abused by incorrect impersonation. This is an arbitrary create bug on the behalf of the .NET framework, which suffered from a similar issue. You can basically, every time that a privileged .NET application ran on your system, which happens quite a lot, you can create arbitrary files in arbitrary locations. Unfortunately, you couldn't alter the content because of bad ACLs, but still, it can be useful. Now, for the second type of exploitation method, I know this is a silly image, but truth to be told, that almost any product that I checked that was created by a PC vendor suffered from DLL hijacking in so many ways. I assume you're familiar with DLL hijacking, so I will speed run through the explanation of it. Now, DLL hijacking is a pretty simple way to inject code. Executables want to load additional code, sometimes on runtime, on initialization. We actually really do not care. The way it works is like this. The application calls load library on the DLL file. We get a H module back, and the DLL is mapped into the application. Soon after that, a function called DLL main will be called, which is unsurprisingly resides inside the DLL binary. This function is supposed to be used for initialization of variables and stuff which similar in nature. But in our case, we just put malicious code inside the DLL, and that's it. Now, this attack is very simple. We just need to put some code inside the DLL process attached. We can completely ignore the other cases. Now, this code will be called immediately after this DLL is being loaded. We can put almost any piece of code that we want in there, although MSDN says that there are limitations, like you cannot load additional DLLs there, and you should not create processes inside there. But actually creating processes inside the DLL main is very safe and very good way to start running your payload, your more complicated payload as an admin or as a local system. Now, there is one main problem in my eyes with DLL hijacking, which is you need to implement tons of export points. Now, if those export points are missing in your DLL, there are chances that, one, it won't be loaded, two, it will immediately crash the host process. And because if we want to execute a shell inside the DLL main, the create process API takes some time on Windows. So our process can die from a critical error because we do not have the export points before we actually gain the ability to execute this shell. But fortunately, there is very elegant solution to this, which is DLL proxy. Now, DLL proxy is a wonderful feature that shouldn't exist in my eyes, that you can specify the linker to forward the request of a given export point to a different DLL. The compiled binary eventually will have a reference to the actual function the DLL was supposed to call. This makes the attack a lot simpler. Just forward the export point to the real DLL and proceed as normal. Now, it's quite easy to generate a bunch of semi-malicious DLLs for every DLL that is being used on the system. Every DLLs that are loaded by services and for other privileged entities as well. So you actually do not need to implement any code whatsoever, just have those pre-made DLLs and plant them in the right place. Now, where is this attack is so useful? Which type of components are so vulnerable to DLL hijacking? Well, installers. Installers are arguably one of the worst software components ever written, and they are prime target to DLL hijackings. And the main reason is that they're almost always privileged. The reason because they are privileged is that they need to do a lot of I/O operations on disk. They install new things, so they write data to new directories, they change values in the registry, they create new directories and files inside the program files or system32 and many stuff similarly. Now, installers are often using outdated installation frameworks, like the Install Shield framework or Setup. Those are just two names that pop into mind. Now, software developers do not emphasize on upgrading the installer. They emphasize on upgrading the thing it installs. The product they install could be very secure, top-notch, bulletproof. But its wrapper software is like a piece of Swiss cheese. In other words, installers can be compared to a diamond ring inside a plastic bag. Yeah, it is that bad. Also, they do not have security checks. Like, they do not check the DLLs that they load to be digitally signed, even for it's an option since Windows Vista. Weirdly enough, even Microsoft that recommends it doesn't do it on their own installers. I checked around 120 installers in my research, and only 4 of them checked if the would-be loaded DLLs are actually digitally signed. Besides that, they are also prime target of symlink attacks, because they create a lot of log files and subdirectories inside the program data. And that's an important thing. Many vendors think that subdirectories inside the program data are admin ACL, but that's not true. So if you prepare in advance your directories there and create a symlink or a DLL, the installer will use this resource and you can easily escalate your privileges. Now, let's see a quick example of it. This is a vulnerability inside the Dell dupe installer. And it goes like this. The dupe is an installer that is created by Dell to provide a unified installation experience to Dell's users, which means it packs lots of software that Dell uses into one installation framework. This installation framework is actually based on the Install Shield installation framework, which is problematic to itself, but never mind. Now, one of the most common mistakes of installers is that they try to load DLLs first from the current directory, which means that if you downloaded a new installer into your downloads folder and you activate it, an administrator activate it, then just placing DLLs there could be a way to hijack into this installer and you can escalate your privileges. Dell thought it will be wise to first copy the installer inside the subdirectory inside program data because they thought it's a secure directory. Now, additionally, they have a random GUID number that is of a directory that is created there. The installer is copied inside the GUID directory, and then it starts executing. Now, as I said, this installer is quite bad because it also tries to load a bunch of DLLs from the current directory. Now, interestingly, a lot of installers that do try to load DLLs from the current directory try to load system created DLLs. that are either in System32 or in syswav64. If you supply them those DLLs, they do not behave any differently if they did not load those DLLs. So as you can see, they suffer from several QA issues that you can easily check them if you check the installer. But as I said, people don't care about their installers, only what there is inside. Now, let's see a quick demo how it works. Now, in this demo, I installed the product on a guest machine from my host, which is, of course, privileged. This is the way those installers are mostly worked in a corporate networks, and I execute it inside the host machine with psexe. Now, I activate a thing called a file watcher, which is watching if new directories are created in the C program data del drivers GUID. And we actually don't care about the GUID because we can get an event when the directory is being created. And we hijack the installers with a DLL named winnienet.dll, and you see that there are two shells that were popping because it actually loaded this DLL and then unloaded this DLL and then reloaded it. So we got two shells with it. So what we can do to combat it. Now, one of the main reasons the installers or other programs are so vulnerable to DLL hijacking is because they use an old API called load library. The load library searches after the DLLs by Windows search and load algorithm, which starts with the current directory and the application directory, unless it's given a full path. But if you use the more advanced and the better API, load library EX, you can do a lot of things. You can supply a flag that will actually prevent the application to immediately call to DLL main. This will make the way of putting exploitation code inside the DLL main completely redundant. Now exploit writers will need to actually really implement some of the exports to hijack the process and run malicious code in that will be reliable. Now, also there is additional flag that is even more useful that guarantees you to only load DLL from system directories, which is C Windows, CWAV64, C Windows System, and the System32 folder. This will, of course, prevent any DLL hijacking attacks unless you have privileges to actually create new DLLs in those folders, which is a thing I think is very good. And of course, you have additional options, and you had the ultimate option of checking if the DLL is digitally signed, which I know it's a bit costly in performance, but installers is a one of a thing, so it should prove no problem. Now, let's go back to MTE and the system that I've developed, which I named Iknaya. Now, after viewing those two exploitation methods, we can ask ourselves, how can we automate the entire loop of finding privileged file operations and how to exploit it automatically? So I developed a system called Iknaya, which tries to implement the whole chain of attack, monitoring, tracing, and exploiting. Iknaya does it automatically, and it comes in two flavors. The first one is concept monitoring. In this mode, we check for every privileged file operations on the operating system that takes place, except some operations from specific processes that we can simply ignore. Through their lifetime, services do actions upon specific triggers, let it be an event or some other behavior. Therefore, sampling each file operations allow us to know if a given service can be abused. In this way, the Windows Defender vulnerability was discovered. The second mode is about checking if a given application is vulnerable to such attacks. The dataset is primarily speaking installers and update programs. As we stated before, installers are mostly executed by administrators. They are also active for a very short period of time, doing their privileged file operations on the initial part of execution. This is how the Dells-Do framework was discovered. You can see that their behavioral profile is a bit different from services. Luckily, it is easier to discover vulnerabilities in such situation because we are not limited to a specific execution sequence that often occurs in services. And the fun part that we actually have an impressive data set of installers that we can constantly fill the CNIA automatically. Another interesting fact is that occasionally the installers will create services that will be later can be re-examined in the first mode. So this cycle continues and continues. Now let's look a bit more on the technical stuff. To monitor a file on Windows, we need to have a software component, a file system driver. In our case, it's a mini filter driver, but it doesn't really matter. It allows us to hook relevant ERPs that can be used to determine if a given application is vulnerable to file manipulation attacks. Those that come from the background of Linux or Mac OS, you do not have ERPs because the architecture of the kernel is quite different. But you can achieve the same things in those platforms as well. Now, ERPs are basically I/O packet data structures that are being used to communicate between drivers and the actual operating systems, and they're transferred from a driver to a driver. Those ERPs are packets that are represented by a single pointer to a data structure instead of many pointers to arguments. ERPs are often queued for easier usage of drivers. The reason that we actually care about them that each file access operation done by a thread is generating an ERP inside the kernel. In other words, every create file operation causes our mini filter driver to receive an ERP. Now, there are three types of ERPs we care about. The first one is mg-create. This is not surprising that triggering a create file operation triggers this ERP. Pretty similar names. So every time you do a create file operation, this ERP will pop. Identifying it allows us to identify places that we can have the arbitrary create primitive, like we can create files in unprotected directories. This is mostly useful while we try to use the symlink attack and while trying to do DLL hijacking. We will see shortly how. The next ERP is mj-write, which is generated, of course, when you do a write operation. This is, of course, can be used also in a symlink attack when we want to create files with arbitrary content. Lastly, there is another ERP with mj-set information. And this is very useful in case we want to achieve arbitrary delete. If you are familiar with the process monitor operations, you can see that they have a bit of similarity because in process monitor, when you want to identify if a file has been deleted, it can be either by set rename or by set information file delete. Information file, sorry. So after catching the ERP, we need to identify if the thread that generated the ERP runs in a privileged context. Luckily, there is an easy way to do it. By calling ZW open thread token EX, we can grab the token and we can check if the privileged user owns it. We do this instead of ZW open process token EX because we want the specific token of the thread and not necessarily the primary token of the process. In the case the thread was impersonated, this helps us to prevent false positives. So what do we do in the driver besides that? First, we log the name, but the path and the command line of the current process, followed by parsing the destination path, which is the path the privileged code is trying to use. This is done by extracting it from the OR packet. Then we continue by calling SE access check on the file with the token of the local guest user. By doing such, we can know if a limited user has access to this file in the end of the path. Now, in the case of a symlink attack, it's not enough to know if we can create files there. We also need to verify that we can delete every file inside the directory and that we have write permissions over the directory itself. Now, if we do have access to this file, we continue to the exploitation phase. To help the driver, I created a local service that implements either DLL hijacking or a symlink attack. The minifilter driver sends to the service the herb type we got. This is important because the way we try to exploit arbitrary create is different than the way we exploit arbitrary write or arbitrary delete. Because on arbitrary create, we create new files. In write, we either create new files or edit existing files. In delete, we just want to delete a file. Then we proceed by impersonating the limited user and create a mount point and a symlink within the impersonated thread of the destination path to guarantee us to mimic the elevation of privilege attack. Since using the token of the local service is not that useful, we need to do it in impersonated context. Now, the service proceeds and checks if this file has been accessed. In case of a write operation, it checks if the file was modified. And in case of delete, well, it just checks if the file is gone. After that, log the result to know if the attack was successful. To monitor and to see the exploitation phase of DLL hijacking automatically is pretty similar. Here, the driver also catches the herb of MJ create. Then it checks if the path ends up with DLL. .dll. Well, I know it sounds a bit of lame, but trust me, it works. I was surprised too. Most of the time that you have a create file operations on a path that ends up with DLL, it will be followed by a load DLL of this path. Now, we can also verify it by hooking the psset load image notify routine, which will notify us whenever a new DLL is being loaded. Lastly, we continue in the same way, by checking if we can write the new DLL into the destination path. Now, we only need here to be able to write the path. We don't care if we cannot delete the files in there. Going back to the service, the driver sends a message to the service with the DLL path and its architecture. You cannot hijack 32-bit processes with a 64-bit DLL and vice versa. You must apply the correct DLL. The service continues by impersonating the local user, like in the symlink exploitation, followed by planting a semi-malicious DLL that does the DLL proxy. If it's a known DLL, it's pretty easy to do it. Otherwise, we just create a DLL with the desired name, hoping it will be loaded and not terminated on the first second that it's being loaded. Now, let's see a quick example of a recent bug that was discovered and fully exploited by Iknaya. This was fixed, I think, in January of this year. Now, this bug is a bit silly. Iknaya caught two herb requests from two different services that did the create file operations on C Windows debug, WYA, or YA tracelog. What were those two services? For starters, I've never heard of those services. They're probably connected on image processing and connecting with image processing devices on Windows. Now, the Windows image accusation is a service that actually ran through in an impersonation context. It has an RPC interface that called the RPC function to impersonate the local user. So it's not that helpful in terms of exploitation. But the still image accusation event, on the other hand, did not do it. So after the create file and the generated herb of MJ create, it can identify the write file on the same path, but with an herb MJ write herb. Now, the write operation was done with anti-authority system, which is very good for us. And in this case, I was able to do arbitrary file creation with arbitrary content, which is basically, in other words, full privilege escalation. So from creating a mount point and a symlink on WYA tracelog on C Windows XT DLL, whenever the service wrote to this tracelog, which is a pretty easy thing to do, this file will be created, and we actually have the possibility to change its ACLs because the service continues to change the ACL of WA trace log to be accessed by any user, which is a rather odd thing. So we just got an NJ write packet. We checked if the owner is privileged, which was indeed this case in this service. We had access to this file. We could also delete actually the WA directory, but by doing such, we needed to wait for the service to recreate it because we do not have access on the parent directory, which is C Windows debug, naturally. We messaged the local service, and the local service did the symlink attack. So if we wrap everything up, if we feed the CNI automatically, we can get a lot more vulnerabilities because it's a fully automatic system. It can be expanded because it only uses now 2 file manipulation attacks, DLL hijacking and object manager symbolic links. If you add additional file system exploitation methods, then I assume the amount of vulnerabilities will be staggering. Now, even by using those 2 methods, there are a lot more bugs to find. And if we look on some numbers, those are some of the CVEs that I got in this research. And this is a bit of a sad slide. You can see that almost every known software vendor was vulnerable to at least one vulnerability of those type of file manipulation attacks. This includes Microsoft, of course, and Google, and many anti-malware vendors, but mostly the vendors that were most prone to those attacks are PC vendors. And that's pretty worrisome because when you buy a new PC, you get tons of shit installed on it that you're not familiar with it. And there are very good chances that right out of the box, your PC is vulnerable to privilege escalation attacks. In addition, those vendors have a very long development cycle, so it often takes around half a month, half a year after first reporting their vulnerabilities before they get patched. In large, if we take on some numbers, 22 vendors were tested in this research, and all of them had at least one vulnerability, more than 60 acknowledged vulnerabilities, and over 100 open cases. Now, a quick recommendation is do not do it from your private email account, the responsible disclosure process. I did it, and I still suffer from it, that I cannot find anything that is not connected to this research. And if there is one thing that I really want you to take from this talk is always do privileged file operations with care. If those vendors did it, none of those bugs could be exploited. And it's not that difficult to do it, and it's not that difficult to create the entire system that was presented here. As I said, I'm not a programmer, I'm a security researcher, so I assume programmers can do a better job than I did. Now, a shout out to a previous work that was done on this field. A lot of applause needs to go to James Forshaw from Project Zero that created awesome tools and many good blogs on this subject. Also, I want to thank IT man, which is named, I think, Clement Labo. I hope I say its name correctly, for his awesome blogs. And there are many others that also written very good blogs about it that I failed to mention. And that's pretty much it. And if you have any questions, I really would like to hear them, either by email or on Twitter. Oh, no. Thank you.
Thank you, Eran. So we did end up with a question, and that is, will using MSI for installers help to mitigate some of the issues?
Actually, yes. Some of the issues are gone, but MSI installer is a pretty old code that there are actually several vulnerabilities inside of it that were published recently. So if you use it on not fully updated machines, there are pretty good chances that it could be exploited as well. But it surely helps.
Okay. Then I think that is all we have. So thank you, Eran, for your talk.